Okay guys, this is where we stopped off last time. We had the car stopped at the light. Light turns green, car hits the gas, and off it goes. Acceleration is constant. We know this because the slope of a VT graph is acceleration. This is a straight line. It's a positive slope. Our displacement time graph was a curve. And this is a little scary to have a curve now. Will you see curved graphs, curved lines and graphs? You will. They can be a little tricky. In order for us to find the area under the curve of this graph, or maybe to find the slope of this graph, we would need something called calculus. So we don't really ask those questions in this course. We only ask slope or area under the curve questions about graphs that look like this right here. So I wouldn't ask you to find the slope or the area under the curve for this graph. Okay. But I can ask you what's going on here, right? So if you think about driving, and I think you've all been in cars, when the light turns green, you start driving, the car has to speed up, which means initially it has a small displacement. And then as the car goes, it gets bigger and bigger. And it moves farther and farther away from the light. And so that's what's going on here. It starts and it doesn't move that far, and then all of a sudden, woo, and it moves really, really, really far. And that's what this graph shows. Here's the thing. These two graphs are connected. They're telling the same story about this car. And you may be asked to draw these graphs. That's a thing. This would be the acceleration time graph. These are the three types of graphs that you will see in this course. DT, VT, and AT. Your AT graphs are all going to be flat lines. I'm telling you right now. Your AT graphs are all flat lines. In this course, we will always have constant acceleration in this course. These will be flat lines. Okay? So, all of these graphs are telling the same story. If I have a flat line here like this, that means I will have a positive slope flat line here. This is a positive slope because this is above this 0 point. So if I have a flat line here, then I will have a straight increasing slope line here. And that means I will have a curved line here. Okay? This is a question I've asked before in class and on the test. Truck blows through a red light at a constant speed. So maybe the person driving that truck has it on cruise and they're not paying attention. Maybe they have headphones on. I've seen people driving with headphones and it scares me because they don't always know what's going on around them. Now at the same time that this person blows through that light, there's a cop sitting there and he tears after that person. Goes. But he was sitting at a stop. So these two cars, when they both pass this light at the same time, and that's when we start our timer. Can you draw the VT and the DT graph for these two different cars, the truck and the cop? So let's think about what's going to happen here. If you take one car at a time, I like the truck because the truck is moving at a constant speed. It's moving at cruise. I find that the easier graph to do is always this second graph, the VT graph. So that truck, if it's moving at a constant speed, its speed is not changing per unit time. So I think that truck is going to have a straight line that's going to go across like this. It's going in the positive directions. It's going to be a straight line going above like this. Now think about what the truck is doing, right? Displacement-wise, as it passes that light and moves away from the light, it's moving at a constant speed. That means that every second, if it's moving at a constant speed, its displacement is changing the same amount every second. That's what it means to be on cruise. If you drive 60 miles per hour, that means after 1 hour you've gone 60 miles. So this is what's going on with the truck. So my truck line will probably be a flat line here, which means what does my line have to be here? It's going to be a straight line going up that way. Remember from the last graphs, if I have a straight line in this graph, I'm going to have a slope here. I'm going to have a curve here. If I have a flat line here for this graph, I'm going to have a straight line like that. So here again, if we're looking at this truck cop thing, if my truck has a flat line in this graph, then it has to have a straight increasing slope line going like that. So my truck line is a flat line that goes like this. Here, my truck line goes straight like that. Now, what about the cop line? Well, I went ahead and shown both of them to you. What is the cop doing? Well, the cop accelerates after the truck at a constant acceleration, which I should have written in here. So at the same time, the cop is starting from zero speed. That's why this VT graph, the cop's line starts here at 0. You know how cops are. They're kind of sitting behind some shrubs or something just waiting to catch you. And the cop car has to accelerate to catch up to the truck. But it's constant, which means that this cop line is going to be a positive slope and it's going to be a straight line. Think about how this works. Some of you have been on the other end of this, right? You see the cop in your rear view mirror and they're coming up behind you. They're having to pick up speed to catch you. And that's what's going on here, is that the cop has to pick up speed in order to catch the person in the truck. So displacement wise, what happens to with the cop? Well, as they pick up speed, the distance traveled is small at first, and then it increases a lot. So the cop line is going to be a curve line here. Okay, so if I have a straight line positive slope in this graph, then I'm going to have a curved line in that graph. I hope that you remember some of these other pictures. That's what happens here. If I have a straight line in this graph, I'm going to have a curve there. So the cop, right, looks just like that last problem. Now, interesting question. What happens right here when these two lines intersect? Do you know? What happens right here is when those two lines are at that same spot, that means that the two speeds briefly are the same. The two speeds are the same. Right here, when those two lines cross, that means, boom, the speed is whatever. It's this. Okay? The cop does not catch the truck at this moment in time. In order for the cop to catch the truck, what has to be true? The cop and the truck have to be at the same place. So the question is, how do you figure out which graph is the best to tell you when the cop and the truck are at the same place? It would be this top graph. And that would be at this point right here. That point right there, the cop and the truck are at the same place. I've actually messed up and I've drawn too much. What's going on here is it looks like the cop is passing the truck. So at this point right here, right there, the cop catches the truck. How do we know? Because look, this is a distance time graph, and at that point, they would both be, boop, at the same displacement at the same time. Okay. Can we tell that with this graph down here? We actually can. That's something that we can actually do. And I'll show you how this works. So here's our graph. This is our VT graph of cop and truck. If you remember, this flat line was truck. This increasing line is cop. All right. Let's say that I ask you, at what point do the cop and the truck, at what point are they at the same place? So what I'm asking you is, what point are the two displacements the same? Okay, how can we figure that out even though we're not looking at a displacement time graph? How can we do this? So the question is, how can we take this graph and get a displacement? Here's the answer. what is the area under the curve of this graph? Slopes mean something, and areas under the curve mean stuff. So what is the area under the curve here? Area under the curve would be velocity times time. And what's velocity times time? It's displacement. It's d. So all I got to do is I have to figure out what are the areas under both of these curves. And I've drawn curves that aren't very good lines, but okay. And I have two curves here, and this really isn't a big deal. Sorry, that's the truck. The truck's curve is this box. So I just have to figure out what is the area of that box. For the cop's shape is this triangle. So what I'd have to do there is I have to figure out what is the area of that triangle. The areas of those two shapes will tell me how far both the cars went. And that's a way to figure out where are they at whatever time is area under the curve. Finally, I thought we'd end with just some practice here. These are just graphing practice. You have some type of a block. There's no friction here. And it is going to slide, looks like down. And can you figure out what all these graphs are? Why is it going to slide down? Force due to gravity, right? So here we go. Can you figure out these three graphs? Displacement time graph, it's going to pick up speed, so it will cover more distance per unit time. So what is this middle back graph going to be? Straight line. Our AT graph is a flat line. We're definitely going to have A because gravity is acting on it, and you know that things will pick up speed due to gravity. If I jump off a tall building, I'm going to pick up speed. It's the same thing here. We don't have any friction. This is going to pick up speed. There we go. How about this? Same thing, right? But it's going in the opposite direction. Whoa, that's weird. It starts away. So now it looks like we're calling this position down here, this is x equals 0. This is our, what we would call our origin. So it's away from that point, and it's going to go to that point, and it's going to pick up speed. So here again, we're going to have a flat line down here. This thing is going to initially not move that far, and then it's going to move really, really far. So it will move more and more displacement as time goes on, as it picks up speed going down the ramp. You see the difference between the first one and this one. This one's wacky. So what's going on here is that this thing is starting at the origin, so it should start right here. But it's already moving. So when we start the timer, it's already moving upwards. It's going to move up and up and up, and somewhere up here it's going to stop. And it's going to come back down. So it's going to start here, and it should end here at the origin. And when it stops up here at the top somewhere, we should have a velocity that crosses this line right here. So what I like to do in this case is I like to say, well, it starts at the origin, so I can put a dot here, and then I know a little while later it's going to be back. It's going to come back down, and I can put another dot right here. And what kind of graph is this going to give me? Something that looks like this. It starts at the origin. At some point it stops at the top. That's what this is briefly. And then comes back down and hits that point again. When it stops at the top, speed is going to be 0. So I know that my speed it's already moving, and then it's going to be 0. So I can put a dot here, and I should get